Howdy howdy, this is Mr. Potter. In today's video we're going to talk about our third type of sort, the selection sort. And the idea behind a selection sort is that we're going to make sure that the first n elements of the list are sorted at any one time. So in other words, as we go through this process, we're going to make sure that the first term is sorted. So I'm looking at 3. You know what? 3 certainly looks like it's sorted. So let's look at 3 and 1. Are those sorted? Well, no, there's some swapping going on. So we're going to swap these. And now this list is sorted. So now let's add the 4. If I put a 4 in here, is this list in order? Yeah, it is. So now if I were to have 1, 3, 4, 1, would this list be in order? And the answer is no, it's not going to be in order. I'm going to have to swap. I'm going to have to swap. And then that's okay. So now that took 2 swaps to get this out. So I had 1 swap over here. I had 2 swaps here. So now if I add the 5, is this list in order? Yeah, it is. If I add the 9, is this list in order? It is. If I add the 2, is this list in order? No, it's not. So I'm going to have to do some swapping again. So the 2 and the 9 get swapped. The 2 and the 5 are going to get swapped. The 2 will get swapped. The 3 and the 2 will get swapped. And the 2 and the 1 won't get swapped. So in other words, in this case, I had 2 swap, 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 swap. This took 4 swaps. Now I add a 6, and that's not in order, so we have a swap and no other swap. So here was 1 more swap. And then this 5, this list is not in order, so I'm going to have to swap, swap, and then that gets the 5 in the right spot. So that's going to take a total of 2 more swaps. That's going to give us 3, 7, 9, 10 swaps. So a total of 10 swaps. Now, that doesn't seem very effective because when we dealt with this before, we said, okay, this 1 would swap with a 3, this 1 would swap with a 3, then the 4 would swap. When we did the selection sort, we actually ended up with 5 swaps, I believe. When we did the bubble sort, we actually ended up with about 20 swaps. And so it looks like this is kind of a middle of the road technique. And in fact, this is going to be worse than the selection sort that we talked about in our previous video. But it does have a very important use, which we will talk about a little bit later. So let's go to the pseudocode and talk about what's actually happening here. So the idea here is I'm going to set my size to the length of my list. I'm going to start looking at box 1 because I'm assuming that if I have 1 element in the list, that element is in order. It's only when I have 2 elements in a list that I really have to do comparisons. And I'm going to compare them. If they're not in the right order, then I need to do a swap. And I'm going to move to the next spot. And I have to do that for each element that I continue to add to the list. So the idea here is I need to make sure a 2-element list is in order. Then I need to make sure that a 3-element list is in order, then a 4-element list, then a 5-element list, and I need to keep going until I get to the whole list. Now again, I could run into a lot of swaps, and if you notice, my worst case scenario is going to look an awful lot like the bubble sort. But there is one place where this really does shine. What this is actually used for is when I already have a sorted list, and I have data that I want to add to that list. In other words, what if I'm not starting at 0, but I make sure that I'm starting at, instead of my pass being 1, what if I make sure my pass is starting at 7? Because I know that the first 6 elements are in order, I just need to start with the 7. Well, let's see. This will swap 3, 3, 3, and that's the correct spot. So I get 1, 2, 3, 4, 5, 7, 8. And now I have 7 elements in order. And what this is really used for is if I want to add unsorted data to a sorted list, I do it at the end. In other words, I just add the data onto the end of the list and then run an insertion sort. And the thing is, it's only going to take that many turns to add it in. If I was dealing with a bubble sort, or even if I was dealing with a selection sort, there's going to be a lot of swapping because this 3 has to swap with the 4. And then this 4 is going to have to swap with the 5. And then the 6 is going to swap with the 7. And then the 7 is going to swap with the 8. And then the 9 will eventually make its way up here, but there's a lot more swapping. With the insertion sort, this is actually a much more effective loop to do, because now this 9 is actually in the right spot already. This is a sorted list. There was no swaps taking place here. So now I need to get the 6 in here, so swap, 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 and there we go. So notice that in order to do this, instead of having the 5 or 6 or 7 swaps that selection sort would have done, I only ended up with about 5 swaps here. This was actually a very efficient way to add data at the end. And so this is what happens. The main purpose of this is not to sort a list that's completely unsorted. The selection sort is much better for that. What this loop actually does efficiently is it deals with adding unsorted data to a sorted list. So that's really where this thing shines. Keep in mind that I do not want to deal with a whole list. The idea is the first part of the list really needs to be sorted. And if the first half of the list is sorted, then we're dealing with the best case, because we're only going to have to add those elements at the end. We always add new unsorted elements at the end. My worst case scenario is going to be the same as bubble sort. In other words, when I have a 9, 8, 7, 6, 5, 4, 3, 2, 1 type scenario, the first step is, of course, this list with just containing a 9 is fine. But now I have to do a swap here. And now I have to do a swap and a swap. Then I'm going to have to do a swap and a swap and a swap and a swap. And I'm going to have to do that all the way through here. Now, I'm only going to have 28 swaps instead of the 56 swaps that I have. So this is still technically better than a bubble sort. But I do run into that issue of, it's just as bad as a bubble sort, because in the way that we coded it, it's almost like a bubble sort. This idea of going and checking spot by spot, swapping spot by spot, and then moving to the next spot. This part here, this whole loop that we've got here, looks almost exactly the same as a bubble sort type swap. So the thing that's important to remember when we're dealing with these sorts is that I want to use the insertion sort if part of my list is already sorted and I just want to add data to the end of it. I don't want to do this as a brute force, this is the first time I'm looking at my data sort. The selection sort is probably the best of the 3 sorts that we've learned so far. This insertion sort that we're talking about for completely random data is actually just as bad as a bubble sort. And that's something to keep in mind. So we've talked about 3 different sorts here. We've talked about the bubble sort, which is the easiest to implement, but it's one of the longest ones to take because of the number of comparisons and the number of swaps that has to take place. We've also talked about the selection sort, which for us is one of the more efficient loops that we've talked about. And we talked about the insertion sort, which if I already have sorted data, adding unsorted data to the elements at the end is going to make this much faster than any of the sorts that we've talked about before. But just given data at the beginning, this isn't going to be the best way. So there are many other sorts that are available. There are some sorts that use recursion, that divide and conquer technique that we learned about for the binary search, that make these sorts much more efficient. But the logic behind them is pretty wacky. And so we're going to leave that for a future computer science course. Understanding these sorts here is probably going to be enough to get us to understand the idea of sorting and how important it is to have sorted data, especially for a binary search. So once again, this is Mr. Potter. Thank you for watching. Have a great day.